Hey YouTube, Stokkill here, and anything that is above absolute zero emits light of some frequency. This may not be light that is visible to us, but it is still light. And light, interestingly enough, is actually a wave and a particle at the same time. But the thing is, when it's in its waveform, it has something called a wavelength, which is probably something that you've seen before, not with your own naked eye, but that you've seen in videos, you've heard about. The wavelength is, well, the difference between two peaks in a wave. So if it looks like this, it's the difference between that peak there and that peak there. That's the wavelength. And then an interesting thing emerges. So of course you can't actually reach absolute zero. Everything has a wavelength because absolute zero is the supertask, which is something I'll talk about in a later video. But basically you keep getting closer and closer to it, but you have more and more energy that you need to take out the system in order to get to absolute zero, and it goes on forever. But anyway, so as an object gets hotter and hotter, its wavelength decreases. It goes from radio waves, which have the longest wavelengths, some of them hundreds of miles long, all the way down to eventually, once you're getting to temperatures such as those inside the sun, where it's plasma, it's a special form of plasma in the core of the sun at least, where the bonds between the neutrons and the protons themselves start to melt apart, and the gluons and the quarks themselves start to melt apart into a soup. That is so hot that it's gamma rays, and these of course are ionizing and they cause cancer. But anyway, the thing is, there is a minimum size in the universe, and this is the Planck length, which is 1.6 times 10 to the negative 35 meters, which is way smaller than any physical thing we've observed. The smallest thing we've actually observed is the electron neutrino. But anyway, as you make something hotter and hotter, its wavelength will get shorter and shorter, of course. But then there's the question of, what if it reaches the Planck length? Because it violates our laws of physics for anything to be smaller than the Planck length. Well, there's kind of an answer to this, but there's also something else which I'll get onto in a second. It would be hotter than temperature. It would be the absolute hot. 142 nonillion degrees, which is a really long number, is how hot it would need to be for the wavelength of a ray emitted, the transverse wave, to be to have a wavelength that was the Planck length, and you couldn't make it any smaller than this according to physics. It would just not be temperature anymore. And I mean, it's debatable if there's even enough energy in the universe for something to reach that temperature. But there's also another point: if you have that much energy concentrated in one area, it will become a black hole. And random pub quiz information for you to store in your memory: a black hole that is formed this way through concentration of energy is called a Kugelblitz.